Okay, we're here looking at gravitational practice number 2, problem number 44. And in this problem, we're on the moon, and a projectile is launched vertically from the surface of the moon, so it rises to an altitude, that's some distance above the surface of the moon, of 325 kilometers, which is equivalent to saying 325,000 meters. We want to know the projectile's initial speed at the launch, and the answer we're given is about 1,030 meters per second. But you notice I put a little asterisk right here. We'll take a look at that in a second. If you take this problem and you throw it into Google, pretty quickly you'll find an answer on it. You'll go to some site like Chegg or what Course Hero or something like that. You'll find an answer, and they'll show you how to do it. They'll say, hey, look, this is an energy problem. You can say that 1/2 mv squared is equal to mgh, and that's not really like the full way to write it. A better way to write it would be that 1/2 m v final squared, which is 0, so vf squared is 0 here, so it goes away, minus the initial velocity squared equals the change in energy. But if they're saying that, if we're on the surface of the moon, they are in this case calling the surface of the moon the reference point of 0, and up here is some height h where we'll get some number. Then we can say mgh here. And what they have pointed out is saying, hey, look, we need to make sure that we find the correct g for the moon. So when they go ahead and solve this problem, they get rid of the m's. They'll ignore the negative for a little bit because they're going to say this is a positive amount here. And in the end, they'll say something along the lines of like vi squared will equal, I bring the 2 over, they'll say 2, and they'll be like, oh, well, I need to make sure I use the right g here. And they'll say g is gm over r squared, and that's the radius of the moon squared, and then times some height, which is this altitude here, right? And if you want to get rid of that square root, we should take the square root of both sides there, and we'll call it a day, right? And if we start plugging in numbers here, we could plug in 2 times 6.67 times 10 to the negative 11th. The mass of the moon is 7.35 times 10 to the 22nd. The height we are is 325 times 10 to the 3, so that gives me thousands. And then divided by the radius of the moon, 1.74 times 10 to the 6th, that's in meters, and we square it. And then we take a big square root of all that thing, whoop, and we'll get a value of about 1030 meters per second. Except this is wrong. And the reason why this is wrong is entirely due to this little g right here, which they have said is gm over r squared. Now there's nothing wrong with that equation, except what they are assuming in this problem is that the amount of gravity you have at the surface of the moon is equivalent to the amount of gravity that you have all the way out here at the edge, wherever we are finishing this problem, at 325,000 meters in elevation. And that's not true. As you move away from the planet, this amount of gravity goes down because this r squared value is always increasing, which since g is given by gm over r squared, if this r squared value here is always increasing, that means the gravitational field is decreasing as you move out. So while the answer in a book is giving you this, that answer is not true. You can't actually use this method to get the correct value. Now, if we think about this for a second, if the gravitational field is getting weaker as I move further and further away, that means I don't actually need all of this velocity to get to this final altitude. I actually need a lesser velocity to get there. Let's actually see how to do this problem properly, which the internet is not going to tell you. So if we go ahead and do this problem properly, what we need to use is a true conservation of energy for a gravitational sense. So we're going to have our 1/2 m, and then here's our vf squared minus vi squared. We know that vf is going to be 0 because we're going to be at our highest point, and we're going to stop at a max altitude. But then it's going to equal gm, where this is the gravitational constant, this is the mass of the moon. And then, there will be another m right here. This is the mass of our satellite or whatever. but we don't care what it is because it's always going to go away. And then multiplied by 1 over the final position minus 1 over the initial position of whatever it is we're launching. Now we need to note two things here. We're not putting this satellite into orbit, so we don't have any orbital energies here. We're just launching it directly off the surface, and it's coming to a stop at some highest point, so we don't need to worry about any orbital energies. And furthermore, we need to be very, very careful whenever we run this right here in parentheses. This is 1 over some final position minus 1 over an initial position. And it's very easy to put these into a calculator incorrectly and just mess something up, okay? So let's kind of clean this up a little bit and put some numbers in here so we see what's going on. I'm going to take this negative stuck in here, and I'm just going to pull it to the outside. So we're going to get negative 1/2 the initial velocity squared, and this initial velocity is what we're looking for. That's our winner. And this is going to equal big G, 6.67 times 10 to the negative 11. The mass of the moon, 7.35 times 10 to the 22nd. And then here's where we need to be super careful. Our final position, if we kind of recall in this diagram up here with the moon, our final position is way out here, which means that we had the radius of the moon plus the altitude that we have to go through. So when we go down here, this value for RF right here, this is going to be the radius of the moon plus 325,000 extra meters. So our figure in the denominator here will actually be 1.74 times 10 to the 6th plus 325,000, which is actually going to be 2065000. Okay, that is our final position. That's all the way out from the center of the moon, all the way out to our high orbit, or our high location rather, because we're not orbiting, minus 1 over, and then this is where we began, which was just the surface of the moon. So this is just going to be 1.74 times 10 to the 6th. Okay, this is the actual setup for the problem. And now all we need to do is go ahead and solve for VI here. What I'm going to do first, because it can get tricky, is I'm going to run this in parentheses here, and I'm going to set it up. The way I'm going to do that is I am physically going to type in my calculator just this beginning part here. I'm just going to type in 1 over 2065000. So 1 divided by 2065000 is 4.84. Oops. Had a moment there. Woof. 4.84 times 10 to the negative 7th minus, and then I'm going to type this section in separately. So 1 divided by 1.74 times 10 to the 6th equals 5.7, and then we'll round up to a 5 times 10 to the negative 7th. Okay, so that is what is actually in parentheses right there. Note that I'm doing 4.84 minus 5.75. They're both the same, times 10 to the. This is actually going to give me a negative value here. And that's actually okay because, and what we want, because I've got a negative on the other side, which is going to cancel out. So if I run the subtraction between these, I know it seems like we're doing a lot just for this, parentheses here, the subtraction, but that's the tricky part. So 4.84, and I'm just going to minus it by 5.75. No, let's just do the whole thing just in case we make a mistake. 4.84 times 10 to the negative 7 minus 5.75 times 10 to the negative 7. This is going to give me here negative 9.1 times 10 to the 8th. And I need to multiply that by the 7.35 times 10 to the 22nd. And I need to multiply that by the 6.67 times 10 to the negative 11th. So let's multiply all those together. So negative 9.1 times 10 to the negative 8th times 7.35 times 10 to the 22nd gives me negative 6.68 times 10 to the 15 times 6.67 times 10 to the negative 11th gives me now, we'll put this in red. Got so many things here. I now have negative 1/2 the initial velocity squared equals negative, let's just do 1, 2, 3, 4, 5. 4.46 times 10 to the 5th. The negatives wipe away like I said they would. Let's multiply by 2 on each side. So we multiply each side by 2. times 2 gives me VI squared equals, and this will be, let's see, what's 4.46 times 2? I don't want to do that in my head. 8.92 times 10 to the 5th. And then now to get rid of the square, we take the square root of each side. And this gives us that our initial velocity really needs to be somewhere around, because we rounded a little bit, 944 meters per second. Okay, so we needed about 100 meters per second less speed here than the original online answer, because they weren't actually considering that this gravitational field here was changing as you elevated away from the lunar surface. That's where they got their 1030, which is technically wrong. We did the problem correctly down here, where by looking at potential energies at different positions and using this energy equation, we were able to say, look, our gravitational field is changing as we move away from the planet, and in doing so, because that field is weakening, we actually didn't need to move as fast in order to get out of that planetary, or that moon, the lunar surface, and get up to the altitude that was needed. Okay, so our final answer there should be somewhere around 940, 950 meters per second, depending on how you rounded things, but it is certainly not 1030. Okay, so if you got the answer of 1030 here, and you're like, hey, look, this is what I found online, or this is what I tried to do, then you made a boo-boo there. That's why I put the asterisk on this. If you went through the whole thing and you're like, I can't get the answer of 1030, that's because the answer wasn't 1030. The answer was 940 something, and you did the problem correctly. So with that, this problem's finished. Don't believe everything you see online, and have a good one. Adios.